All right, this part of the assignment is for the reading. And before I go into the reading and some of the things I would take notes on, I'm going to do a quick recap of the end of the last reading, which is the structure of equation. And in this, we have reactants are always on the left side and the products are on the right. And this arrow means the chemical reaction, the yields. So if two things are put together, like let's say wood and oxygen, they will react, they will catch fire, and they are going to produce some things like CO2 and water vapor. So we have to keep this structure in mind as we go through today's reading. So we're going to start with conservation of mass. So if I highlight something for us to take notes on, I will let you know, and you should add them to your notes. No matter how many reactants and products are involved, all the atoms present at the start of a reaction are present at the end. Think about what happens when classes change at your school. A class is made up of a group of students and a teacher together in one room. When the bell rings, people from each class move from room to room, ending up in different classes. The number of students and teachers in the school has not changed, but their arrangement is different and the new groups interact differently. I think that's a great analogy for how atoms rearrange. If you think about my first hour, my fourth hour, you guys all get up and go to different places. You are now restructured. So now you have a new class that you go to, similar to chemical reactions. We take old substances and we get a new substance. We're going to come back to this picture in a little bit. Now imagine that all the students and teachers are atoms, and each class is a molecule. At the end of a reaction, similar to a class change, the same atoms are present, but they are grouped together in different molecules. The amount of matter in a chemical reaction does not change. Therefore, the total mass of the reactants must equal the total mass of the products. I would definitely record all of these bolded statements as we go along. This is the concept, the principle called conservation of mass. This is super important for us in chemistry. So I'm going to reread it. The amount of matter in a chemical reaction does not change. Therefore, the total mass of the reactants must equal the total mass of the products. So this is called the principle of conservation of mass. And it means that during a chemical reaction, matter is not created or destroyed. So let's go back to this picture. Notice it said conservation of mass. So they have scales here which measure mass. So we have iron on this scale. And yeah, iron is black like that. We always think of iron as being like a shiny metal, but it does come that way. All right. And then we have sulfur. Sulfur is a yellow like that. Sulfur is what's in gunpowder and firecrackers. So if you've ever had that smell of a firework going off, it's more than likely the sulfur that you're smelling. All right, so let's look at the conservation of mass. We have 14 grams of iron plus 8 grams of sulfur. We heat them up, they react, they turn into iron sulfide. So if we could zoom in, we'd see it's a different substance. And what do we notice? There's 22 grams here, which would make sense. Matter is not created or destroyed. 14 grams plus 8 grams is 22 grams. So 22 grams on this side of the reactants and 22 grams on the products. Matter was not created or destroyed. At first glance, some reactions seem to violate the principle of conservation of mass. If you measured the cooled ash left from a wood fire, for example, it wouldn't have the same mass as the wood that had been burned. What happened to the missing mass? So let's go up here and think about that. We had a fire in a fireplace. We were throwing in pieces of wood that were real heavy, and at the very end, all we have is light powdery ash. Think of what happened to that mass. Where did that mass go? I'll let you think about that for about 20 or 30 seconds. So how many of you thought it left as the smoke and the gases that came off the fire? If you thought so, that was the right answer. Much of it escaped, much of it meaning the mass. So much of the mass escaped into the air as carbon dioxide gas and water vapor. Yeah, water vapor comes off. Anytime you burn something, water vapor is given off. How many people have noticed a car exhaust in the wintertime seems to have like this cloud coming out of it? Well, that's not really the the pollutants. Most of it is water vapor coming out of the exhaust. So if you could trap and measure these gases, you'd be able to prove that the mass didn't change. So our checkpoint here: how do the numbers and masses of the atoms in the reactants of a chemical reaction compare with the atoms in the product? So now they're talking not so much about the mass, but about the numbers of atoms. So let's take a look. In this equation, we had one iron atom plus one sulfur atom. And on this side, we had one iron atom and one sulfur atom. The amount of atoms was the same. Sometimes that's not the case, and then we have to balance them. So this next section is on balancing chemical equations. So what does the principle of conservation of mass mean for a chemical equation? Matter is not created or destroyed in a reaction. This means that the same number of atoms exist in the products as in the reactants. So let's stop and think about that. What they're saying is, if there's hydrogen on the reactant side, and there's two of them, then we need two of them on the product side. And if those numbers are not equal, we need to somehow make them equal, which we're going to get into. So matter is not created or destroyed in a reaction. This means that the same number of atoms exist in the products as in the reactants. To accurately describe a reaction, a chemical equation must show the same number of each type of atom on both sides of the equation. When it does, chemists say the equation is balanced. To balance an equation, first look at the formulas. So we have H2 plus O2 yields H2O. How many atoms does an oxygen molecule have? So this is your oxygen molecule. How many atoms of oxygen are there? There's two. How about hydrogen? There's a hydrogen molecule. It has two as well. How many of each kind of atom are present in one water molecule? So this is one water molecule, and what we have is H2. So we have two hydrogens, and we have one oxygen. So right now, this is not balanced. I have two on this side and only one on this side. So we need to balance that. Now let's look at this in a little bit more visual way and go through the process of balancing. So if we take a look at the chemical equation and models for the reaction, so there's your H2. They are given a blue color for the atoms. And the O2, they're given a red color. And you see that there's two atoms there and two atoms there. Now when we go to the H2O, we notice that there's only one oxygen atom and two hydrogen. So count the number of atoms of each element on each side of the equation. You'll find two atoms of oxygen in the reactants, but only one atom of oxygen in the products. How can you get the number of oxygen molecules on both sides to be the same? You might be tempted to balance the oxygen by changing the formula for water to H2O2. Notice they tried to change this by putting in a subscript of 2 there. Well, now we no longer have H2O, we would have H2O2. Don't even think about it. Remember that H2O2 is the formula for hydrogen peroxide, a completely different compound. To balance the equation, we're going to use just coefficients. So what is a coefficient again? A coefficient, remember, is the number in front of a compound or a molecule. So we're going to start changing these in order to get the right total. A coefficient is a number placed in front of a chemical formula in the equation. It tells you how many atoms or molecules of each reactant and product take part in the reaction. So that's our ratio that we're going to start dealing with. If the coefficient is 1, you don't need to write it. Balance the number of oxygen atoms by writing the coefficient of 2 for water. So here's what they did there. They noticed that there's 2 O's on this side, and there's only 1 O on this side. So what did they do? They put a 2 there. And by putting a 2 here, now there's 2 O's, 1 and 2, but it changed something else. It also changed the hydrogens. So now there's 2 times 2, which gives us 4 total hydrogens. So now there's something else unbalanced. Now the hydrogen's unbalanced. 4 on this side and 2 on this side. So okay, you've balanced the oxygen atoms, but now there are 2 hydrogen atoms in the reactants and 4 in the product. How can you balance the hydrogen? Well, let's try doubling the number of hydrogen atoms on the left side of the equation by changing the coefficient for hydrogen to 2. So that's totally fine. We can totally add a coefficient of 2 here and make something else unbalanced that was balanced, and then we can go ahead and rebalance it on this side. It's a lot like your math class when you're dealing with algebra, trying to do some algebraic equations. You can change both sides. So now there are 4 hydrogen atoms, 1, 2, 3, 4, because we put a coefficient of 2 there, and 2 oxygen atoms on each side of the equation. The equation is balanced. 4 hydrogens, 4 hydrogens, 2 oxygens, 2 oxygens. And this is our division here between our reactants and our products. It tells you that 2 molecules of hydrogen, right there, react with 1 molecule of oxygen, right there, to yield or give you 2 molecules of water. Count the atoms in the last diagram. Prove to yourself that the balanced equation is correct. So that is it. So let's go through what I would take as the notes. All right, so in the conservation of mass, I would have this bolded statement. The amount of matter in a chemical reaction does not change. Therefore, the total mass of the reactants must equal the total mass of the products. I would have that. I would also have that the total number of atoms on the reactant side must equal the total number of atoms on the product side. I would have that as well. It's a little twist on this same concept or principle. All right, I would have, when it comes to balancing equations, I would have that we need to only add coefficients. So I would put in there, to balance chemical equations, we can only change the coefficient. And then I would also add that we have a total number of atoms on the reactant side equals the total number on the product side. And I'll give you more as we go tomorrow in the notes on balancing chemical equations, and also with carrying out some balancing equations. Dad. John? Hold on, Nana.